Parallelizing LLM training requires more than adding accelerators. Devices may wait for memory, exchange data inefficiently, or repeat model state that could be divided. I'm Mehrdad. In this lesson, we will diagnose that waiting, examine the main parallel training methods one at a time, explain how FlashAttention reduces memory movement, and use lower numeric precision without losing training stability. Suppose two teams train the same model on the same tokens using 8 identical accelerators. One team completes an epoch in almost half the time. The slower run keeps complete copies of model state that could be divided, sends frequent messages across slower connections, and leaves some devices idle while others finish. During each step, every accelerator reads parameters and activations from main device memory, writes intermediate results for the backward pass, and exchanges data before the next computation can begin. Peak hardware throughput describes fast mathematical operations under ideal conditions. It does not include every wait for memory or another device. Model math utilization measures how much of that theoretical model computation the run actually achieves, but it is not a universal target across models and clusters. Start with completed step time. Then separate time spent computing, moving data through memory, communicating between devices, and waiting at synchronization points. Also inspect memory used by parameters, optimizer state, gradients, and saved activations. Measure first, then divide the limiting object. Adding more devices before finding the limit can increase communication and make the run slower. If this explanation is useful, like the video and subscribe to follow the series. 5 parallel methods each divide a different training object: the batch, layer matrices, layer groups, repeated model state, or token positions. The next 5 slides take these methods one at a time. After that, we will add expert routing as a separate distribution pattern for mixture of experts models. These methods can be combined, but they do not solve the same constraint. This overview is a decision map, not a recipe. Identify whether the run is limited by batch throughput, model width, model depth, repeated model state, or sequence length. Then choose the method that divides that object and account for the communication it introduces. Data parallelism places a complete model replica on each worker and gives each worker a different part of the training batch. Every worker performs its own forward and backward pass. The workers then combine their gradients, usually with an all-reduce operation, so every replica applies the same update. This method is effective when one model replica fits on each worker and a larger global batch improves throughput. Its main communication event is gradient synchronization. Slow links or one delayed worker can make every other worker wait at that point. Increasing the worker count also increases the global batch unless the batch per worker becomes smaller. That can change optimization behavior. Measure examples processed per second, gradient synchronization time, and the effect of the global batch on convergence. Data parallelism divides examples. It does not reduce the memory required for one complete model replica. Tensor parallelism is useful when a layer is too wide or its matrix operations are too large for one device. The system divides a large matrix calculation across several devices. Each device computes one partition of the result, and the partitions are exchanged or combined before later operations can continue. This communication happens repeatedly inside transformer layers, so tensor parallel workers usually need fast, high-bandwidth connections. Placing them across a slow network can turn every layer into a communication barrier. Tensor parallelism can reduce the memory and computation assigned to each device for wide layers, but it also makes the layer depend on collective communication. Measure the time spent in matrix computation and in those collectives. Keep a tensor parallel group inside the fastest connection domain when possible. This method divides layer calculations. It does not divide the training batch or remove pipeline imbalance. Pipeline parallelism places consecutive groups of transformer layers on different devices. The first stage processes the input and sends its activations to the next stage. Later stages continue the forward pass, and gradients move back through the stages during backward computation. To keep several stages active, the batch is divided into smaller microbatches that move through the pipeline at different times. Empty periods at the beginning and end form a pipeline bubble. An uneven layer assignment creates more waiting because the fastest stages must wait for the slowest one. Pipeline parallelism helps when model depth or the memory for many layers is the limit. Its cost is stage-to-stage activation transfer and scheduling complexity. Measure each stage time, the size of transferred activations, and the fraction of time each stage is idle. Balance the stages before adding more of them. Standard data parallelism repeats parameters, gradients, and optimizer state on every worker. Full-state sharding divides those three categories across the workers instead. A worker gathers the parameter pieces required for the current layer, performs its computation, and later releases or reshares data according to the software schedule. This can make a much larger model fit because no worker permanently stores every copy of the full training state. Fully sharded data parallel and zero stage 3 belong to this broad family. They share the idea of sharding complete model state, but their execution schedules and implementation details are not identical. The memory saving comes with extra communication and temporary buffers during gather, compute, and reshard operations. Measure peak memory, communication volume, and completed step time together. Full-state sharding solves repeated model state memory. It does not automatically solve activation memory from long sequences. Long sequences create large activations and expensive attention calculations, even when the model itself fits. Context parallelism divides token positions from one sequence across several devices. Each device stores and processes a portion of the sequence, while communication supplies the information needed to compute attention across portions. This differs from data parallelism because the devices cooperate on one long example instead of processing different examples. The exact communication pattern depends on the attention implementation and training framework. Moving query, key, value, or partial attention data between devices can become the new limit. Context parallelism is useful when sequence length or attention memory prevents the example from fitting efficiently on one worker. Measure memory per device, communication per attention layer, and step time as the sequence grows. This method divides token positions. It does not make attention local unless the model architecture explicitly uses a local attention pattern. Mixture of experts models introduce another distribution problem. Different feed-forward experts can live on different devices. A router selects one or more experts for each token. The system groups tokens by destination and sends each group to the device that stores the required expert. After computation, the results return to the devices continuing the transformer layer. This creates an outward transfer and a return transfer for every expert layer. If too many tokens choose one expert, that device becomes overloaded while other experts wait. If token groups cross slow network links, communication can remove the computation savings from activating only part of the model. Expert parallelism distributes experts and routes token groups between devices. Measure tokens per expert, transfer time in both directions, and idle time while results return. Efficient routing needs balanced expert demand and topology-aware placement. Standard attention conceptually compares every query position with every key position, producing a large matrix of scores. A straightforward implementation may write that matrix to main device memory and read it again during later operations. For long sequences, moving the matrix can take more time than parts of the computation. FlashAttention reorganizes the same calculation into blocks that fit in faster memory close to the processor. Each block loads a subset of queries, keys, and values, computes partial attention results, and updates the output without storing the full score matrix in main memory. The softmax remains exact. FlashAttention uses an online softmax update. A running maximum and normalization total let each new block update the probabilities consistently with the complete matrix calculation. FlashAttention changes the order and location of operations, not the mathematical result. It improves efficiency by reducing reads and writes through slower memory. The benefit grows with sequence length because the avoided score matrix grows with the number of token positions. An attention implementation tuned for one accelerator generation may perform poorly on the next. Compute units, shared memory, data transfer engines, and instruction schedules do not all improve at the same rate. FlashAttention versions adapt block sizes and operation schedules to the balance of the target hardware. The first version established the exact block-by-block method that reduces main memory traffic. FlashAttention 3 overlaps more data movement with computation and includes an 8-bit attention path for supported Hopper hardware. FlashAttention 4 reorganizes the work for Blackwell hardware and highlights a 16-bit path. Version 4 is not simply the 8-bit version 3 implementation copied onto a newer chip. Its schedule accounts for hardware units whose speeds changed by different amounts. The broader lesson is that kernel performance depends on matching data flow to the accelerator's memory and compute structure. Confirm which implementation, numeric format, and hardware generation your training stack supports. Lower numeric precision stores each value with fewer bits and can make supported matrix operations faster. The reduced number range and rounding detail can also destabilize training. bfloat 16 is a common starting point because it reduces memory compared with full precision while retaining a wide numeric range. Some large training systems perform selected operations with 8-bit floating point values. They keep sensitive calculations, accumulations, normalization values, or other model-specific components at a wider precision. This is mixed precision training because different values use different formats within one step. 8-bit formats also differ in scaling and rounding, so a recipe designed for one software and hardware combination may not transfer directly to another. Begin with a stable, wider precision run. Move specific high-cost operations to 8-bit computation only when the hardware supports them and the measured benefit is meaningful. Monitor training loss, gradient magnitude, overflow events, and held-out evaluations. Lower precision succeeds only when it reduces memory or step time without unacceptable behavior changes. 2 additional controls help when activation memory or communication limits the training step. Activation checkpointing stores only selected intermediate results from the forward pass. During backward computation, the system recomputes missing activations when needed. This trades additional computation for lower memory use and may allow a larger model, sequence, or batch to fit. Communication overlap addresses a different limit. The scheduler begins exchanging gradients or model state while a device performs independent computation. Effective overlap hides part of the transfer time behind useful work. It cannot help when the next computation immediately needs the missing data, or when the network remains overloaded. Evaluate both controls through completed step time. Check how much extra computation checkpointing adds, how much communication remains exposed, and how long devices wait at synchronization points. Also inspect whether repeated model state, an unbalanced pipeline, or a poorly placed tensor parallel group created the original problem. Apply the control that addresses the measured wait instead of enabling every feature at once. Remember 3 decisions from this lesson. First, measure completed step time and identify whether memory movement, communication, or idle time is limiting the run. Second, divide the object that creates the constraint. That object may be the batch, layer calculations, layer groups, repeated model state, token positions, or experts. Third, optimize the remaining computation with methods that preserve the required result. FlashAttention keeps exact attention while moving less data, and lower precision needs hardware support plus stability checks. Parallel methods can be combined, but every added dimension introduces communication and scheduling cost. Begin with the smallest combination that fits the model and shortens measured step time. I'm Mehrdad. Next, supervised fine-tuning changes how a base model responds to prompt and answer demonstrations. We will examine answer token masking and evaluation in video 17. I'll see you there.